Hello and welcome to the fourth in this series of blogs on the systems approach to project management, and this one deals with systems thinking and beyond for project managers. So what I'm going to do here is explain systems thinking, to show you some of the benefits of systems thinking, to show that there are different incomplete versions of systems thinking in the literature, where systems thinking is appropriate, and why you have to go beyond systems thinking to solve the problems, provide you with a useful thinking tool, and this time I'm not going to try and complete it in less than 15 minutes because I want to keep it all together so you can find it in one place. So the topics in this snippet are: what is systems thinking, the benefits of systems thinking, the perspectives perimeter, which is the tool, and the holistic thinking perspectives that are points on the perspective perimeter. So what is systems thinking? Well, if you look in the literature, if you look it up on the internet, you'll find that the answer depends. It depends on who you read. Some people will tell you that it's thinking about a system as a whole, and that we apply to the product or the system, and that is systemic thinking. Other people will tell you it's employing a methodical step-by-step manner, and that is generally a process, and that's what managers do. They follow the problem-solving process. Well, first they create it in the planning phase, and then in the doing phase they follow it, and sometimes they modify it as and when problems show up. That is systematic thinking. And the more knowledgeable systems thinkers will tell you that systems thinking is in a systemic and systematic manner. That is, you have to think about the product and the process. And these are generally the systems thinkers who perceive the system from more than one perspective. And I'll tell you about the benefits of that shortly. And then what I call holistic thinking, which is systems thinking and beyond, and that is the combination of systems thinking, analysis, and critical thinking. So let's take a look at systemic and systematic thinking. Systematic thinking is used to create and follow the problem-solving process for the project. So in the planning phase, you use systematic thinking. You follow a little process to create the plan, and then the process is what you follow for the rest of the project, and it basically also follows the problem-solving process. Systemic thinking is used in the problem-solving process for gaining an understanding of the undesirable situation, identifying the causes of the undesirability, conceptualizing the problems, conceptualizing the solutions to the problem, and then verifying that the solution has solved the problem, and so on. So why use systemic thinking, or what's in it for you? Well, my first answer comes from about 1735. When people know a number of things and one of them understands how the things are systematically characterized and related, that person has an advantage over the others who don't have the same understanding. And how about this one? 250 years later, people who learn to read situations from different theoretical points of view have an advantage over those committed to a fixed position, for they are better able to recognize the limitations of a given perspective. They can see how situations and problems can be framed and reframed in different ways, allowing new kinds of solutions to emerge. So, why use systemic thinking? And what's in it for you? You have an advantage over the competition. That's what's in it for you. And let's take a look at this graphically. Perspectives of an issue. Here you can see a system or an issue, and Sherlock, our project manager, is in there, and he's looking at the various elements within the system. And notice that there are blind spots. He cannot see much of the triangle because it's blocked by the black circle. So Sherlock is smart. What does he do? Well, he moves over to another viewpoint in the system, and he perceives the system from the other viewpoint. And he's smart, so he realizes that he has to go outside the system and take a look from more than one viewpoint. And so he's smart, and he realizes that he has to look at the system or the issues for a number of different viewpoints. And the only element of systems thinking that looked at something from a set of standard viewpoints was the work of Barry Richmond in his 7 streams. So we took the work of Barry Richmond and expanded it into the perspectives perimeter. This is, we consider the issue or the situation as a 2-dimensional representation and draw a circle around it. And then we look at the issue or situation from points on that circle. Have you ever been in a situation where you'll hear somebody say, let's make sure we're on the same page? Or the engineers will say, let's make sure we're on the same wavelength. At least the communication, the electronic engineers might say that. What they're actually doing with that statement is trying to position themselves at the same point on the perspectives perimeter. And so based on the work of Barry Richmond, I've come up with 9 perspectives. The external, internal, progressive, and remaining perspectives. External are big picture and operational. Internal are functional and structural. Progressive are generic, continuum, and temporal. And remaining are the quantitative and the scientific perspectives. So briefly, the external perspectives, the big picture gives you the context for the system and any assumptions. The operational perspective is what the system does. It's a black box perspective. And this is where causal loops come in. There are some authors who will equate system thinking is causal loops. Much of Peter Senge's work in the 5th discipline in causal loops is fine, but it's not systems thinking, at least the entire systems thinking. It's only a part of systems thinking. And then you have the internal perspectives, the functional perspectives of what the system does and how it does it. That's a white box perspective, as we say in engineering, and that also uses causal loops. And you need to distinguish between operational causal loops and functional causal loops and not mix them together. That gives you artificial complexity. And the other internal perspective is the structural perspective of how the system is constructed and organized. And the progressive perspective, this is where you go beyond systems thinking. The generic perspective is where the system is perceived as an instance of a class of similar systems. Your system is similar to another system, and that system might be out of your box. So when you're looking at that other system, or you've got somebody in your team who's familiar with that other system, this is where the out-of-the-box ideas might come from. And similarly, the continuum perspective, this is the opposite of generic. This is where you look at the differences between your system or your situation and other situations. And again, this is where your out-of-the-box ideas will come from. And then there's the temporal perspective, where you look at the past, present, and the future. What happened in the past to give rise to the situation? And what's the future if nothing is changed? And even if something is changed, what's the perceived future likely to be? And the remaining perspectives are the quantitative and scientific perspectives. The quantitative perspective is the numeric and other quantitative information associated with the system, and the scientific perspective is prescriptive. The previous 8 are all descriptives, those perspectives are what you see. The scientific perspective is what you infer. And that's the hypothesis or guess about the issue, cause, problem, and solution. So let's look at them in a little more detail. The big picture. You call it a helicopter view or a bird's eye view, and it's a static view. It contains the purpose of the system, the environment and the context, the adjacent systems, and the assumptions that you're making. And you can see here my view. And what I've done in this view is I've abstracted out the internal aspects of all the systems in the picture. And I'm complying with Miller's rule, the magic number 7 plus or minus 2. The operational perspective. That is the external or a black box view. It's a dynamic view. You look at the missions or the operations performed by the system. So this is what the system does, how it's used. You document this in scenarios or use cases. And here we use causal loops or feedback loops. The same thing depends on whether you're using the thinking terminology or the engineering terminology. And we think about the desired and undesired inputs and outputs. For example, an undesired output is waste. And so we need to get that into our drawing. And everything inside the system boundary is hidden in this view. And so here's my operational thinking test. Where's the coffee? I was at a conference in Israel, and it was a coffee break, and I wanted a cup of coffee. So I walk over to where the refreshments are, and I see these two containers. One of them contains hot water and one of them contains coffee. So from an operational perspective, my question to you is, which one of them contains the coffee? The assumption is you don't know any Hebrew and you have to think it through. You're not allowed to go over there and pour a little out, and you're not allowed to ask anybody. Can you work out from an operational perspective which one contains the coffee? From a functional perspective, that's an internal or white box view. This is the closed system view, whereas the external operational perspective is the open system view. It's a dynamic view. It's the functions performed by the system, how the system works. Again, the causal or feedback loops of the internal interactions. And everything outside the system boundary is hidden in this view. And these are the functions that are used in the scenarios. And let me explain the myth of open and closed systems. The myth, you look in the literature, and people will tell you that there are two different types of systems. The reality, from the holistic thinking perspective, is there are really two views of the same system. The closed system, internal white box view, is the functions performed by the system and the structure. The open system is the external or black box view, big picture, metasystems and adjacent systems, and the operational missions and the operations performed by the system. So how did the myth arise? Well, I think the myth arose because there was only one view used for that type of system, and so it became categorized as that type of system. So, for example, a pendulum clock is generally treated as a closed system. But it's only a closed system if you're looking at the pendulum and the other elements of the system, because the effect of gravity is constant as long as you stay on Earth. If you move your clock to the moon and you forget to change the weights because gravity is different, your clock will not work. And let me give you an example. Consider docking in space. This is the International Space Station. This is the US Space Shuttle, and it was used as a supply vehicle, and we used to dock it with the International Space Station. But when we're dealing with the problem of docking to the International Space Station, what we do is we construct a closed system. we abstract out everything other than information pertinent to the relative positions of the spacecraft, the relative velocity, and the relative alignment in orientation, so that when the two vehicles come together, they're aligned so that the docking collar just snaps together and it's slow enough that no damage is caused, but it's fast enough so that the thing will fit together properly. And this is a sub-problem of transferring cargo from Earth to the International Space Station. And what we do with complex problems is we break it up into simpler problems. And so problem 1 was move the vehicle from Earth to near the space station, and the second problem was dock the vehicle to the space station. Moving on to the structural perspective. That's an internal structure of the system. It's a static view. We deal with the architecture framework. We deal with the components. That's the technology and their availability. The information. That's the content of the information and the dependability of the information. Is it accurate? Is it timely? And the people. They're parts of the system. The type of people we need and their availability as resources, and the internal subsystem boundaries and partitions. And I've showed you a structural view here on the slide. And here's a structural view of holistic thinking. You can see that holistic thinking is made up of internal, external, progressive, and remaining perspectives. Systems thinking generally deals with the big picture and the operational external perspectives. Analysis deals with the internal, functional and structural perspectives. Quantitative perspective infuses everything else because it puts numbers on the functions, on the scenarios, on the elements in the structure, and so on. And critical thinking is used to validate the thinking in all of the other perspectives. Now, some of the systems thinkers will tell you you don't need the analysis. You should focus on systems thinking. Well, that's true and false. It depends on what you're trying to understand. I saw one video on the internet that talked about water. And water is made up of hydrogen and oxygen, but if you're trying to understand wetness, then you have to think of water as a whole and understand wetness as a characteristic of water as a complete thing. Well, that's true. But if you're trying to understand the chemical interaction between water and phosphorus, then you need to understand what water is made up of, the elements. And so, which perspectives you use depend on what it is you're trying to understand, on what the problem is. So the information in all the perspectives may or may not be relevant to the particular issue that you have at hand, but the perspective perimeter and the holistic thinking perspectives give you a framework for viewing the issues and storing the information that you view. So the generic perspective is where you go beyond systems thinking. It talks about similarities to the other systems. So your system is an instance of a class type of system. So for example, a cargo ship is a surface ship. A car is a land vehicle. And here you can observe patterns of behavior and inheritance. And so something behaves like, something looks like. And so our example for docking in space, I can show the problem breakdown structure. The International Space Station resupply problem breaks out into two problems: ground to orbit, get the spacecraft from ground into orbit near the ISS, and then once it's in orbit, orbit to duct. Generically, this is a similar problem to the one golfers experience. Do they go for a hole in one, or do they go for a hole in two? And they break it down into first get the ball onto the green, and then once they're on the green, then putt it and into the hole, into the cup. And if they're lucky, they can get a hole in one. So this is where generic thinking helps you come up with a solution to the ISS problem and helps you break it out into two sub-problems which are similar to the problems that the engineer had in playing golf. The out-of-the-box solution came from the golf cup. Well, I'm not saying it came from it, but it's similar. Another example, you can see here two generic displays of information, one at an airport, one at a railway station. They use different technology, but in functional language, they provide information about departures to specific destinations to tell the traveler where to go to catch the transportation to the specific destination. And so I'll give you another thinking test. Use generic thinking. Where's the coffee? Again, which one of those containers contains the coffee? And this is where you use the generic perspective. And again, both the operational perspective, or the answer to the operational perspective, and the answer to the generic perspective questions are based on making an assumption and then inferring from that assumption. And if you make a different assumption in the operational perspective and you make to the one in the generic perspective and you come up with the same answer, then there is a much higher probability of your inference being correct. The continuum perspective. This is where you look at the differences to the other systems. This shows you a range of solutions. It's gray rather than black and white. And here you see that either or solutions are only 2 points on a continuum of solutions. One size doesn't fit all. Things are situational. More than one theory can coexist simultaneously. Changing conditions may cause movement along the continuum, and it gives you the ability to deal with ambiguity. And if you're a real good holistic thinker, you see ambiguities where other people don't. And sometimes you see humor and you will make poor jokes. Now, as a manager, this is a very important characteristic to have, because when you're giving instructions to people or you're writing a contract, you need to take out the ambiguity and to make sure that what you write is interpreted in the same way as you interpret it. The temporal perspective deals with how the system behaves over time. So elements of the past, present, and future, and patterns of behavior. This leads to the concept of prevention. In the systems area, it leads to the concepts of availability, maintenance, logistics. Looking into the future, it talks about obsolescence. Looking into the past, lessons learned. It opens your mind to new thoughts, because you realize that the current paradigm, or the way we do things today, is not necessarily the same way that we did things a year ago, 2 years ago, 10 years ago, and so on. And it's not necessarily the way we're going to do things in the future. So it opens your mind to the possibility of change and the effect of change. The quantitative perspective deals with numbers. And as Barry Richmond said, They must be useful, not necessarily perfect. They don't need to be absolute. You can look at relative positions. You can see analog rather than digital. It deals with quantification rather than measurement. It helps to understand the scope of relationships. In causal loops show you the relationships, but they don't tell you the magnitude of each item in the causal loop. The quantitative perspective helps you understand the magnitude, and so when you combine causal loops into models and simulations, the quantitative perspectives gives you the value. And it deals with ordering and ranking, and the Pareto principle or the 80-20 rule is a good example of the quantitative perspective. And lastly, we come to the scientific perspective. After you've gained an understanding of the situation from the other perspectives, you then filter out the pertinent information and you come up with a hypothesis or a guess or a design or a research question, depending on what it is you're doing. And remember, when you come up with a design, it's really a guess, because until you've actually built it and tested it, you don't know whether the design is going to solve the problem. And the scientists don't like to tell you this, but it's very similar to trial and error. Because you say, oh, I think the cause is this. And then you do something to remove that cause, and you take a look again and say, is the situation still undesirable? Well, it may or may not be. You may have identified the wrong cause, or you may only have identified a partial cause. And so then you need to go around the loop, the problem-solving loop again, as I talked about in a previous video. And let me give you an example of some linked perspectives. Let's look at transportation. So in the big picture, we're talking about the road network, the cars drive the economy, and so on. From an operational perspective, we use cars to go shopping, take the children to school, and other scenarios. In the functional perspectives, we're traveling from place to place, so we're starting the car, stopping the car, turning to the left, turning to the right, moving forward, and so on. From the structural perspective, we have a car with 4 doors, a chassis, 6 wheels, and a boot or a trunk, as they say in the United States. 6 wheels? Where did that come from? Well, you know about 4 wheels, and what do you steer it with? And do you have a spare? 6 wheels. Generic perspective, and let's talk about 4-wheeled land vehicle. And so generically there are similar vehicles, trucks, vans, and so on. From the continuum perspective, we might look at different types of engines and different types of vehicles, land and non-land, and so on. From the temporal perspective, we look at cars that came before and cars in the future. So the Stanley Steamer, the Ford Model T, and then there are different types of engines that we used in the past. The internal combustion, the external combustion, steam engines, electrical engines, and so on. Or the Ford Edsel, hybrid cars that we see at the moment, at the present time, and then future all-electric cars, and so on. In the quantitative perspective, we'd come up with numbers, miles per hour or kilometers per hour, engine power, number of passengers, cost, price, and so on. Now, what we infer on the scientific perspective will depend on the problem or issue that we're dealing with, and which information from which perspective is pertinent, again, depends on the problem or the issue. But when we're doing the brainstorming or the thinking to try and understand the situation, lots of ideas will come up. And we can store them and then use them as appropriate. And so an example of applying holistic thinking to the system or product being designed, we generally think about the normal operation, and that's the operational and the functional perspective. But we also need to consider abnormal operation, and so here we combine continuum operational and continuum functional perspective. So the continual operational perspective says, well, what about accidents? What about externally induced failures? And so with a vehicle example, we can say, well, what's the effect of an accident where another vehicle will smash into this vehicle and break something? And do we have to strengthen a part of the vehicle to take care of that? And this doesn't only apply to, this applies to commercial as well as military systems. And we can also think about process failures. What happens if this machine fails? Or what happens if part of the machine fails? What will that do to our production line? And the continuum functional perspective, that deals with internal failures. And we need to consider those. And so our abnormal, accident, and failure prevention and mitigation, functional is what can happen. We talk about a failure effects mode analysis, and that deals with internal damage due to aging components. And sometimes components age simply because of the physics. Rubber, for example, ages whether you use it or not. So if you're going to put rubber into a system in the form of gaskets or something else, you then need to consider your spare parts situation if the system is going to have a long life. Because if you buy all your rubber spare parts at the beginning of life of the system, when you put it into service, by the time you actually need to replace the rubber components in service, you're going to have to replace the rubber in your spares. And the operational perspective, what can happen? And that's what we call fault tree analysis. Internal interaction with the operator. What happens if the operator screws up? What about externally induced failures? What about misuse? And so on. And then from the temporal perspective, the lessons learned. What happens in the past? If you're upgrading a system, then what needs to be improved this time around? Talk to the operators, talk to the users, and find out what they'd like changed. You may not be able to do it because it may cost too much or it may not be feasible, but at least talk to them and find out. And what about the lessons learned from similar systems? Before you do something, look at similar systems and see what lessons you can learn from them. And so here's another question I have for you. You can learn from the generic perspective. This is the sign at the Hiyoshi subway station in Yokohama. If you look at the sign, there are three languages. The first, or there are three languages, yeah. The sign at the top is three symbols in Japanese katakana script. He, yo, and she. And then you've got English, Hiyoshi. And then you've got kanji, which is pictographic. And you've got 2 syllables for a 3-syllable word. And then comes Korean. And at the bottom, you have the 2 syllables in kanji repeated. So my question to you is, tell me how to pronounce the symbol that the arrow points to, that looks like a square number 8 or a door. Is it Hio or is it he? All the information you need to answer the question is staring at you in the face, assuming you're looking at the screen. What's the benefit? Well, the benefit of going beyond systems thinking shows up in this chart. The factors conducive to innovation depend on the ability to find similarities among objects which seem to be different, and the ability to find differences among objects which seem to be similar. This doesn't come from systems thinking. This comes from going beyond systems thinking from the generic and the continuum perspectives. Or if you are a problem solver, then you have a high ability to find similarities among objects which seem to be different, and a low ability to find differences among objects which seem to be similar. And if you're a problem formulator, then you have a high ability to find differences among objects which seem to be similar, and a low ability to find similarities among objects which seem to be different. And if you're an innovator, then you're high in both abilities. So what are you? And can you develop those skills if you're not? So, I met the objectives. I explained systems thinking. I showed you the benefits of systems thinking. I talked about different incomplete versions of systems thinking and why you have to go beyond systems thinking and where systems thinking is appropriate. And I provided you with a useful thinking tool, the perspectives perimeter. And I didn't try and complete it in 15 minutes. So, questions and comments in the usual place. And if you've got this far and you've watched all the way to the end, in my book, Holistic Thinking, I expand on an awful lot of what's in here and more, and what's in the previous snippets. And if you send an email to me at the email address on the first slide, I will send you a URL where you can download a PDF version of this book that's printable, and information about how you can order a paper copy at a 30% discount. Thank you for watching this presentation. I hope you've enjoyed it, and I hope you've learned something.